Hello, I'm back with another demo video for MLP, that is machine learning in practice. This is a huge subject. We are going to look at a problem statement and we will go through the workflow. Let's begin. So, the problem statement is there is a wine company. That wine company wants to develop a ML model to predict their wine quality based on certain features so that they can replace their expensive quality sensor. So basically we have to develop a ML model that can predict the wine quality. So what's the workflow? First we will look at the bigger picture, get the data, we'll discover and visualize the data to gain some insights. We'll prepare the data for the machine learning algorithms. We will select a model and train it and fine tune the model. We'll present our solution and at last we will launch, monitor and maintain our system. So what's the bigger picture? Bigger picture is we have to understand what we have and what the problem statement is about. So what's the input and our output? What algorithms we are going to work with? Is it a regression or a classification problem? So first, our input is some features. For example, pH level, density, etc. We are going to look at it. Output is the wine quality. Now this wine quality is a regression problem. Why? Because it has continuous values and does not have discrete labels. So basically we are dealing with some regression problem. What algorithms we are going to use? We will be going to use linear regression, decision trees and random forest. Yes, we will be working with three algorithms and at last we will pick the best model that gives the best predictions. So let's look at all these algorithms. What is linear regression? So linear regression is a curve fitting supervised learning algorithm. What it does? So as per the name, linear regression is forms a linear function like this, f of x equals to ax plus w. So it assumes that the features and the target column has a linear relationship. It creates a line that fits the data points and give us a prediction. So the intuition is draw a line that best fits the data. Let's move to decision trees. Now what is decision trees? It is a tree structure. It has a root. It starts with the roots. It has edges. These are nodes. And the last node is called the leaf node. So it asks a series of questions to reach the final decision. So I have given an example over here. We have to understand that whether a person will like a strong tea or a light tea. We will basically have two features, that is the tea leaves and the sugar. So we will analyze on basis of how much tea leaves or how much sugar does he likes in his coffee. So it goes like sugar. Does he add sugar? Yes or no? If no, that means he likes strong tea. If yes, then how much? Similarly, tea leaves, how much? 2 spoons, 4 spoons, and this goes on. Now, decision trees are usually large, so they have a tendency to overfit. Now, what is overfitting? We will learn it in the later chapter. So, random forest. Random forest works with ensemble machine learning algorithm. So, basically, random forest consists decision trees. Let's say it has n number of decision trees. It train each tree on different samples. Then test each tree independently. Each tree gives some result. The final output is the majority answer or the average of all the predictions. So basically it combines all the predictions. Now random forest reduces the problem of overfitting. So these are the three algorithms that we are going to work with. Let's proceed. Now here are some libraries that we are going to need. First is import numpy as NP. NumPy is a package in Python that is used for data calculation, mainly for the NumPy array. We have import pandas as PD. Pandas is also a Python library we have for data manipulation. We have Matplotlib and Seaborn. Both are visualization libraries, but Seaborn is slightly advanced and gives statistical information as well. Let's look at some functions. These are the basic functions. First, we have pd.readCSV data URL. This is to get the data. So, readCSV will read the CSV file from this particular URL that we are going to provide. Now, data.head in bracket we have x. Data.head will give the x number of records from the first data set. So, basically, it will give first x records from the data. Now, if there is no parameter provided, by default, it will show the first 5 records. In data.tail, it will give the x records from the last of the data set. If there is no parameter given, by default, it will show the last 5 records. Data.info, it will give information about the data set. So basically, data.head will look like this. It will, let's see, no parameter is given. So it gives the first 5 records. We can also see the features over here. Fixed acidity, volatile acidity, like this. And we have this quality column, that is our target column. Now data.info, it gives information. What information? So we can see that it has, the data set has 1599 entries, that is 1599 records that are indexed from 0 to 1598. It has total 12 columns, and these are the features or the columns. Now, these are the number of non-null values. So we can see that there is 1599 non-null values. That means throughout the data set, we don't have any null value. Also, it shows the data type of each column. So we have float 64 like this, and the last, that the quality column has int64 data type. Okay, so we have now data.describe. It gives a statistical description of the data set. And by default, it gives the numerical columns. So let's see data.describe. So we have the feature names over here, and you can see it gives count, mean, standard deviation, minimum value, like this. So for fixed acidity, the count is 1599, mean is 18.31, standard deviation is 1.7. So like this, it gives the statistical description of the whole data set. Okay, so let's see the remaining two. We have data feature name dot unique values. This unique values function will give a list of all the unique values in this particular column or the feature name. Now data feature name dot value counts. This value counts will give the unique records along with their frequency. So how many those unique values are present, it will give those frequency. Let's proceed. Domain knowledge. So before going deep into the machine learning and the dataset, we need to know that what this dataset is about, what those particular columns or features is. So domain knowledge is really important to understand the significance of each feature. We can do that by consulting the experts. So let's see. We have features like fixed acidity, and this is the significance. So most acids involved with wine or fixed or non-volatile do not evaporate readily. We have volatile acidity, citric acidity, like this. Okay, let's move to splitting the data. So we have the whole data set. Now from this whole data set, we want to split the data set into two, one for training and one for testing. Usually we do it in a 80-20 proportion. It can also be 70-30 like this. But the majority of the data goes for training and a few percentage goes to testing. Splitting of data, we can do it by two types. One is random sampling and another is stratified sampling. So random sampling, it randomly selects k percent points in the test data. So basically from the data set, it will randomly, let's say, pick up 20% of the data for testing. But in stratified sampling, it will pick up 20% of the data, but it will maintain the overall distribution of the data set. So for example, let's say in the data set, 50% is category A and 50% is category B. So it will maintain those distribution. It will split the data in training and testing such that in training there is 50% A and 50% B. Also in testing there is 50% A and 50% B. But in random sampling, the distribution is not maintained or it is not ensured. So let's see. From sklearn.model selection, sklearn is a package that is scikit-learn. We are going to import train test split. So train set test set equals to train set split. This data is the name of the data set. Test size we are going to mention it as 0.2. That is 20% for testing and 80% for training. Random state 42. So this is a random sampling and we are mentioning random state equals to 42. So basically it will do random sampling, but 42 ensures that whatever randomly taken samples are taken at this 42 state, it will remain same in this state of 42. If any other state is used, like let's say random state 12, those examples will be different. So it ensures that each time those same examples are taken. And yes, this number can be anything. It can be 0, it can be 1, it can be 100 as well. Let's move to data visualization. Okay, so this is important that we first do the train test split. That is, we first split the data into training and testing and then we move to data visualization. Why? Because we do data visualization only on the training data and not on the testing data. Because if we do the visualization on the testing data as well, it will lead to leakage of information and may lead to what is called snooping bias. So it will leak the behavior and pattern of the testing data. And we don't want that. So let's see. First we have a histogram. How we plot a histogram? For this we are using matplotlib. So sns.set data.quality.hist. So data is the name of the data set. Quality is the column that we are going to visualize. And hist is the histogram. PLT, that is the matplotlib. X label is wine quality. So in x-axis, we are naming it as wine quality. And Y label is count. That's the frequency. So we are plotting a histogram. In x-axis, we have the quality feature column. And in y-axis, we are going to have the frequency. So you can see that for a quality 3, it has a frequency below 100. For 4, it is below 100, but in the middle, it's around 50 to 60 frequency. From 6, 5, and in between 6, it achieves a frequency more than 650. For a quality 6, it achieves something around 650. For quality 7, it is exactly 200, like this. So this histogram tells us that the quality is higher in 5 and 6. This is the majority classes, and it also tells us that our data set is imbalanced. It is not balanced over all the classes. Let's move to scatter plot. Now, what is a scatter plot? So, it looks something like this. It's two-dimensional. We are working with density and fixed acidity. It tells us the trend, whether it's going up, down, or there is no such pattern. So here we can clearly see that it is going up. That is, the trend is upwards. So if the fixed acidity increases, the quality also increases. This is the pattern. We plot it using Seaborn. SNS.scatter plot. X equals to fixed acidity. So we mention the X. In x-axis we want fixed acidity. In y-axis we want the density. Hue equals to quality. What is hue? That is a color code. So you can see quality. So if it is 3, it is the lightest color, and if it is 8, it is the darkest color or violet. So from 3 to 8, the color varies. Data equals to exploration set. What is the exploration set? So we have divided our data set into training and testing. The training is the exploration set that we have named. Okay. Now, let's move to correlation and heat map. So in statistics, we know correlation. So if correlation equals to positive 1, it is strongly correlated. If it is 0, it is not correlated, and if it is negative 1, it is negatively correlated. So basically it tells the correlation between the features. We can calculate it by, we have given CORR underscore matrix equals to data dot CORR, data dot cor. So this will give us the correlation value. Now we are going to plot it. So plotting the correlation in a heat map. What is a heat map? So it looks like this. It is a tabular data where the correlation is mapped with the respective features. So you can see that for fixed acidity and fixed acidity, so both are same, so it gives a correlation value 1 and it is the lightest color. So in the diagonals, these are all 1s because they are correlated to each other, the same features. And we can also see the values of the correlations. This is the color. So we can say that if it is strongly correlated nearer to 1, it is the lightest, and if it is negatively correlated strongly, the last is dark violet. How to plot it? So plt.figure fixed size 14:7. So we are mentioning the size of this. So the length is 14 and the width is 7. SNS.heatmap, we are providing the correlation matrix and not equals to true. That means we are setting that annotations equals to true. So these values pops up. So this is all about heat map. We can see we have some correlated features. Density with fixed acidity is highly correlated. We also have citric acid with fixed acidity. Yes, these are the highly correlated. Also, we have quality with quality with alcohol. And yes, something like this. Now, there is another option to visual the relation between the features, that is scatter matrix. So this is a scatter matrix and we can plot it by pandas. So from pandas.plotting, we import a scatter matrix. This is the attribute list. That is the features that we want to see. So we have mentioned citric acid, pH, alcohol, sulfates, quality. Scatter matrix, the exploration set, that is the training set. and we have provided the attribute list. And this is how it's going to look. It is going to tell the pattern of both the features, how they are related to each other. Now, the objective is to get a quick insights into the features and its relationship with other features and labels. We usually document these insights in a Word file or a PDF file that we are going to see it later. Okay. Let's move to data preprocessing. First, why we preprocess the data? Because the data set that we first load is a messy and a raw data set. Machine can't understand that. So we need to preprocess it, clean the data set, and then we are going to feed it to the model. So what are the steps we are going to use? First, we will separate the features and the labels. That is the features and the target column. Features are like the features are like the alcohol, sulfates, chlorides. Label is the quality column. Then we are going to handle the missing values and outliers. Now, what are missing values? So, let's say in a column, there is a null value. So, no value is typed in or entered. In that case, what we do? First, to find out if there is a missing value or not, we use isNA.sum or isNull.sum. This will give us the summation of all the null values. In this data set, we currently don't have any null values. But if there is, either we can remove it or we have to impute it with its mean or median. So mean or median imputation. Now, when we use mean if there is no outliers present. So no extreme value is present, so we can impute it with the mean. If outliers are present, we impute it with the median. And median is the safest option. Next is feature scaling to bring all features on the same scale. So what is feature scaling? So let's say one column ranges from 1 to 20 and the next column ranges from 100 to 200. Now these scales or the ranges are very different. It becomes difficult for the model to analyze and it may become biased. So we makes the range similar. There are two ways we can do that. One is min-max scaler. It ranges the whole data set, the columns, from 0 to 1. So the minimum value takes the 0th position and the maximum value takes the 1st position. And all the values comes in between. Standard scaler is the minimum value takes -3, maximum +3. Also, since it's a standard scalar, the mean will be approximately 0 and the standard deviation should be approximately 1. Okay, next is applying certain transformations like log, square root on the features. Why? To correct the skewness. So if a column is highly right skewed or left skewed, we can apply this transformation to make it a little bit like a normal distribution. Okay. So how we are going to separate our features and the label? We can use the drop function. Here in wine features, we have used the training dataset dot drop quality comma axis 1. So basically we have dropped the quality. Axis 1 ensures that it drops from the column wise. If we use axis 0, it works on row wise. So we have dropped the quality column and stored all the other features in the wine features. So we have also used a wine labels where we have copied only the quality column. So basically now we have a wine features where we have a data set of all the features columns and we have a wine labels where we have only the target column or the quality column. Okay, let's come to encoder. So in this data set we have all numeric values, but in a data set we can also have categorical values, textual data. So in that case, we need to encode it. We have two type of encoder. Ordinal encoder, one-hot encoder. Also there is a label encoder. Let's see what it is. So encoder is basically we will transform our textual data into numeric values. What is ordinal encoder? Ordinal encoder has order. So let's say we have a column that consists size. We have small, L and XL. So small is marked as 0, L is marked as 1 and XL is marked as 2. So it has order. So from smaller to larger, it increases. This is ordinal encoder. What is one-hot encoder? One-hot encoder, it creates dummy columns. So let's say we have a column of gender where we have male, female, female, male. What it will do? It will create dummy columns of those labels. So male and female. And then it will mark 1 or 0 if male is present, so it will mark 1 in the male column and 0. If female, in the female column, it will mark 0 in the male record and 1 in the female record. Like this. Now, why both are there and when to use? We use ordinal encoder if we have an order in our column, like the size. Let's say we have male and female. We can't place it in an ordinal encoder because we don't have any order in male and female. If we do that, the model can be biased towards the higher number, 1. We use one-hot encoder when there is no order, but this usually increases the complexity of the model since its size increases. We also have a label encoder, so it just places zeros and ones randomly without any order. This is how we can implement it. From from sklearn.preprocessing, we import ordinal encoder, and we are capturing all the functions into this ordinal encoder, and we can call it on the particular column. We have to call the fit transform function. Similarly, we can get the one-hot encoder from the sklearn preprocessing. Okay. Now let's move forward to column transformer and pipeline. Here's an important topic. What is a column transformer? So basically, we have to do a set of data cleaning, pre-processing, and all this can be stacked up so that we don't have to manually do it every time. So let's say we are doing on the training dataset. We have to again do it on the testing dataset so that to match the input that we are feeding to the model. We can build a pipeline or a column transformer. What is a column transformer? So it basically, we provide a set of transformations. Here you can see we have provided num attributes, one-hot encoder. So basically we are going to provide a set of transformations with its column names where it is going to apply. So column transformer will apply this each transformation to its appropriate column, and then it will concatenate or merge all the input along the columns and will give us a whole data set at last. So it works column wise. Let's see pipeline. A pipeline doesn't works column wise. What it will do? We will give a set of instructions like transformations in a sequence. It will work in a sequence. So it will, let's say, first we have a imputation. So first it will impute in the whole data set, and then it will pass that data set next function like standard scalar. So it will pass the data set, not the columns. So at the end we will get a data set that is transformed. So in column transformer, we mention the column names that we want to transform. In pipeline, we just mention the name that we are going to give and the function that we want to apply on the whole data set. Let's move to model training. So now we have already got the data. We cleaned it, we preprocessed it, we have seen encoders, column transformer pipelines, and finally we are going to train our model. Okay, so now let's come to model training. So I have given an example of linear regression. So from scikit-learn.linear model, we are going to import linear regression. In linreg, I have stored all the functionalities of linear regression. Now we are going to call the fit function. Linreg.fit wine features and wine labels. Fit is the function that is going to fit the x and y axis that we are providing into the model and train it. Now wine features is the training features that we have stored. Wine labels is the training labels. That's the target column. Basically our quality. After training, we are going to call the predict function. In ypred, I am storing model.predict. Model is basically the model that we are using. Here we can say linreg or linear regression. Dot predict x test. What is the x test? X test is the testing data. The features of the testing data we were providing in this predict function. What it will give? It will give us a data set or an array of predictions. Next come model evaluation. So now we have to evaluate that whether the predictions that are given are accurate or is it good. Now we have two ways. For regression, we can use MSE and MAE. For classification, we use accuracy score, precision score, recall and F1 score. These are some model evaluation techniques. There are a lot more, like we have RMSE for regression, R2 score. For classification, we also have a confusion matrix, but we are not delving too deep into it. So basically, we have to choose a evaluation technique and we have to evaluate our model, how good it is doing. Okay, now let's come to cross validation. We have already evaluated our model using some evaluation techniques. But cross validation provides a robust way of model evaluation. How? So it basically creates n number of samples of the training data and it evaluates those samples and gives us an average evaluation score. So basically, let's say we have 5 samples. Each 5 samples will go for training and testing. And it will give us some score, evaluation score. And at the end, the output is the average of all those scores. How we are going to implement? Scores equals to cross-val score. We have used the model linreg, that is a linear regression. We have provided wine features, that is a training set. Wine labels, that is the training labels. Scoring, we have given a scoring function. CV equals to 10 means how many samples we want. So 10 samples we want. And we have got a ultimate average score. So this is a much efficient way for evaluating a model. So next, what is model diagnosis? Now we have to understand that whether our model is underfitted, overfitted, or it is a generalized model. After all this evaluation, if our prediction, that is the test prediction, comes lower than the training predictions, then we have to understand that our model is underfitted. That means it does good on training data, but it does not do well on testing data. So it's basically like an exam. It cheats in the training. So it gets a better score in the training phase, but in the testing, it fails. That is overfitting. So how can we reduce overfitting? First, we can use a simpler model, or we can feed the model with large data. We can feed the model with more data or more constants or regularization. What is underfitting? That is the opposite of overfitting. So basically, it does not do well in training, but all of a sudden it does good in testing. This is suspicious, right? If it is not training good, then how it is doing performing well in the testing? So in that case, We can use model that has more capacity, and we can use less constraints or regularization. Or we can also try using a complex model. Let's move to fine tuning. Now, what is fine tuning? After all this evaluation, now we want to fine tune our model. That is, basically, we want to optimize our model, optimize our model's hyperparameters. So, what are hyperparameters? Hyperparameters are some experimented values or parameters. Let's say we have max features. So max feature is a hyperparameter, is the number of features, maximum number of features we want. Also we have max depth. Max depth is the maximum depth that we want in our decision trees. Okay, we have max iter, that is maximum iterations of learning or training we want. We are not going too deep into the hyperparameters, but let's see how we can optimize it. We have two ways. We can use grid search CV or randomized search CV. What is grid search CV? So basically we have to provide a param grid, a list of parameters that we want to fine tune. Okay. Now grid search CV, what it will do? It will find the best combination of hyperparameters by testing all the possible combinations. So let's say here we have n estimators, max features, bootstrap, and all of this. It will try all these combinations. Let's say n estimator 3 with max features 2 and like this, and find the best combination. Yes, it is of course extremely time consuming. And that's why we come with randomized search CV. Randomized search CV will also give the best combination of hyperparameters, but it will test the necessary combinations. Or it will pick some random combinations, and among those random combinations it will give the best combination. Yes, grid search CV will give the optimal solution, but randomized search CV will also give a good combination, but it is more efficient and good if time is a constraint. Okay. Now we move to analysis of best model and its errors. So we have to analyze our models and their errors. We have to understand that which features are important to the model. So what features the model is using for actually predicting the value. For that, we have taken feature importance equals to grid search dot best estimator dot feature importances. So we use this feature importances function to get the features that are important to the model. So what we have? So at top we can see alcohol is the most important feature. Then comes sulfates, then come volatile acid, and at last we have pre-sulfate dioxide like this. Now why we want to see that? First, for presentation, key features. Second, we may also drop the features that are not so important. So you can see alcohol gives us a score of 0.24, but free sulfur dioxide gives a score of 0.04. So that's relatively lower. We may want to remove these features when in case that is increasing our model complexity or we have too many features. Okay, it is also useful to analyze the errors in prediction and understand its causes and fix them. So by looking at it, we can understand that which features the model is prioritizing, and through that feature, we can understand why it is giving such predictions. Now comes evaluation on test set. So after all this fine tuning and optimizations, we will evaluate our final model on the testing set. So we have to transform our test features, like I said earlier. That's why we use column transformers or a pipeline. So we have to run all those transformation on the testing set now. Transformation in a sense, we have to clean the data, and if we have done ordinal encoding or some encoding, we have to do that on testing set as well. So just like the way our training set went into the model, the testing set should be a replica of that. Otherwise, the model will not understand. So for that, we use a transform function. For uh, for training data, we use a split transform, and for testing data, we use just transform. Split transform will capture all the patterns of the training data, and transform will apply those structures or patterns into the testing data for predictions. So at last, we will predict using the predict function, and we will give our testing features. And we get our final evaluation. We have used MSE, mean squared error. Okay, in every evaluation, we have to give two parameters. First is our testing predictions, that is the predictions given by the model, and our actual predictions. So we are getting an MSE score of 0.35. So we have completed our model. Now we come to presenting our solution. So once we have our best model, so after all this evaluation, we will know that which model is working. So we have tested on three models: linear regression, random forest, and decision trees. By looking at our MSE score, the model that is going to have the highest MSE score, we are going to pick that one. And now we are going to present our solution. So basically, we have to highlight our learnings, our assumptions, and our limitations. Also, we have to create visuals and present the model. So we usually create visuals using this Matplotlib and Seaborn. Also, we have for presentation, we have Power BI and Tableau. Now, at last it comes launch, monitor, maintain your system. Launch is basically we have to plug in all our input sources and write the test cases. Monitoring, system outrages, degradation of model performance, sampling predictions for human evaluation, regular assessment of data quality, which is critical for model performance. So let's say we have deployed it, and now we have to continuously monitor it, that how our model is performing with the real world data. Maintenance, we have to train our model regularly at every fixed interval with fresh data. Why? Otherwise our model may become outdated. Production rollout of the model. And we have reached the end of this video. And again, this video does not contain the whole MLP. We have more concepts like dataset APIs, regularizations, ridge regression, lasso regression, and etc. So this is a video containing an overview of the MLP and just the workflow. And that's the end. Goodbye for today.